So I am delighted to invite Mark to this talk. In fact, it wasn't me that invited Mark, it was Jamie Rattray. So unfortunately, Jamie's in the field, so it's fallen on me to introduce Mark. So this is based on, correct me if I get anything wrong, Mark, but it's based on a research project from University of Strathclyde on fluorosis and variation in fluoride across catchments with different water supplies, with the impact that has on the local population with that drinking water. I'm sure you will give it a lot more detail than that. But yeah, if I can hand over to Mark, away you go. Thanks.
Thank you. Hi, everyone. Okay, so my name is Mark. What I'm essentially going to be showing you today is the entirety of my PhD project, which has just finished a couple of months ago. Specifically the geogenic and the geological and the hydrogeological aspect of it. There was a big sort of policy aspect of it, which I'll kind of briefly cover just to give some context, but I'll not go into too much detail about that stuff. So just a bit of background. So groundwater fluoride is a global water degradation issue affecting about 200 million people globally. The UN and UNICEF's joint monitoring program have recently classified it alongside arsenic as a priority chemical contaminant of concern alongside arsenic. I think that was in 2017. So countries aiming towards SDGs targets, specifically SDG 6 for clean water and sanitation. This is going to be a big focus for those countries because it affects so many people. Malawi is a country which has quite a lot of, I'll quantify that better later on, but there are fluoride and fluorosis problems in Malawi, but they're not very well understood, and I'll get into that a little bit later on. But so far, the background from Malawi's perspective in terms of achieving this goal is that they don't really have much knowledge. There's quite a vacuum of knowledge pertaining to fluoride in the country, and the links to human health with fluorosis are very, very few and far between. There wasn't much there to go on. And finally, they're untreated drinking water fluoride standard. So the World Health Organization set a standard of 1.5 milligrams per litre in drinking water. So for a consistent use, that's the threshold, that's the maximum threshold. Anything above that is considered fluorosis causing with increasing severity. But Malawi's standard is still set at 6 milligrams per litre, which is significantly higher. So that's out of date, essentially. So that's a bit of background as to where the project began. So the aim there was to develop, so before I actually say that, it was to develop a new creative and cost-effective national solution for Malawi to predict groundwater fluoride occurrence, which makes the best use of existing, which is often sporadic, data. So there are numerous complex ways where you can create GIS risk models using comprehensive and vast data sets with all sorts of different types of data that cover vast areas. There was an example in India where someone took groundwater from groundwater samples and climate data and a vast array of different data sources which covered the entire country and created a really complex risk model, which is not possible in Malawi. The reason being that the data just doesn't exist. It's very sporadic and the understanding is pretty low. So I wanted to come up with something that was cost effective, something that's going to cost a lot of money or take a long period of time to execute, and it makes the best use of the data that already exists. So why, as I've just said, it's to assist Malawi to achieve SDG 6 within the time frame. So we've only got less than 10 years left, 9 years left before the deadline. So the push is really on in this final part of the SDG time frame. As I've said about the GMP classification as a priority chemical contaminant. So in order for Malawi to achieve SDG 6, this is really important that they achieve this. When I say this, I mean a way to mitigate the damage and to assess current groundwater assets for fluoride. To document fluoride occurrence and its health effects, because it's relatively undocumented. Right now, it's mostly just local scale studies. There's nothing national has been attempted. And to also demonstrate that fluoride prediction for SDG tracking is possible with limited resources globally. So the methodology here, I split into a 4-stage process: evaluate, develop, adapt, and then finally refine and validate. Now, the little image I've just put on the right-hand side is that I've taken that from my thesis, so that's why it has chapter numbers, but it's really just there to give you an idea of how this methodology developed. So evaluate would be, as I mentioned before, there wasn't much information there to begin with, so my first stage was a desk study. I had to evaluate exactly what is known in Malawi, what data is there, what analysis has already been, what's the national understanding, and what do I have to work with, and what are the knowledge gaps, essentially. Obviously, the purpose of this was to develop a method by which we can predict or at least screen for groundwater fluoride, so that the Malawian government have a tool going forward. So the second stage was to begin to develop that via a case study. It was a local scale case study where I basically developed the initial idea of how I was going to predict, how I was going to create this prediction method, and then obviously with human health implications and eventually going national with this method, it was important to try to quantify the human health risk link, which hasn't really been done before. So that was attempted, and I'll go into more detail when I get to that section. The third stage is adapt and scale. So basically, the method that was developed is then attempted, or it was actually adapted to cover the entire country so that it works on a national scale, so that the government can use that as a tool. I also done a fair analysis of fluoride policy in Malawi relative to global policy and World Health Organization limits, etc. And I came up with a proposal for them to reduce their groundwater fluoride standard over time. I'll not go into too much details about that, although I am happy to answer questions on that. And then finally, to refine and validate the method. So there was, by the time we got to the end, I got to the end of the third stage, it's something, lots of assumptions are made to make something simplistic work on a national scale. So there are various ways which this method can be refined. So I chose the most obvious and most significant way, and done another study to attempt to refine the method overall, which was successful, and I'll go into that again. And then just to validate it, each of these stages was published as separate papers. So the fourth paper, the refine and validate paper, was actually a collaboration with a team of dentists from the University of Glasgow, which was an odd sounding collaboration, but you'll find the results quite exciting, I think. And that was essentially to validate the human health risk assessment, which had been done before, and that's necessary to advocate policy review. Okay, so the first stage, evaluate. So this was essentially a desk study. You all know what a desk study is. It's just a literature review and a data collation. I had to gather together everything that existed that I could find pertaining to fluoride and fluorosis in Malawi. So on the left-hand side, we've got some examples of where some of this information came from. This one here, Malawi Hydrogeological and Water Quality Atlas, is something that the government of Malawi released internally, I think in 2018. It didn't have data, but it did have maps with various water quality parameters, and they were mapped where the water point was. They were mapped spatially, and then they were coloured either above or below the threshold, or their own, depending on their own limits for each of those things. So for example, fluoride was either above or below 6 milligrams per litre, so it was a red triangle or a green triangle. So that's an idea of the quality of some of the data that I was working with. So sometimes it's not so good, sometimes it's excellent. This here is a report done, or at least it was conducted by the BGS in 1980 by a man called Adrian Bath. That was probably the most comprehensive study that I came across. It was a general groundwater quality survey, which took into account many different things, one of those things being fluoride measurements and what may or may not be the cause. So that was one of the better data sets that I got. And I'll go into a little bit more about the quality of that data later, and then obviously some publications which I found from internet searches that had actual data contained, which I could extract and then use. So on the right hand side, this is a summary of basically everything I managed to gather in relative to Malawi itself and where these things occur. So a bit of geological background. On the left-hand side here, you've got the East African Rift System. So you've got the eastern branch, which stretches from Ethiopia down through Kenya to Tanzania. And then you have the western branch, which stretches from Uganda down to southern Malawi and into Mozambique. The map on the right-hand side is a map of Malawi, and it just shows you the expression of the Rift Valley in Malawi, and it's significant for this first part. So most of this part here that I'm just about to talk about, this evaluate section, most of that data that you see from this slide on the right-hand side, the majority of it exists within the southern region here. So I tend to think of the Rift Valley in two parts in Malawi. You have this part here, the top 2/3, which is submerged beneath Lake Malawi, and then you have the bottom third, which is this kind of Z shape here, which is an onshore expression of the Rift Valley. So I tend to think of these as two separate Rift Valley environments within Malawi, but that's the expression of the Rift Valley there, just to give some geological context to the study. Okay, so I'll just go straight into the data. I don't want to spend too much time talking about the data itself, because there was a lot behind the scenes of cleaning the data and comparing it with new data and trying to essentially cleanse it as much as possible to try and glean as much quality information from the data as I possibly could. But this was essentially the result. So once I had got rid of data, for example, that had huge ion imbalances or consistent errors in some data sets were maybe removed because there was a consistent error suspected, but I couldn't prove it. So this is the cleanest data that was left, and that's what I'll work with through the rest of this section. So I've split it here, I've plotted it, fluoride against calcium. So this is important because fluoride in groundwater exists under certain conditions, and the ratio of calcium often determines the ratio of fluoride, which is able to exist in dissolution in groundwater, and that's controlled by the fluorite equilibrium. Fluorite is a fluoride mineral, fluoride calcium mineral. So I've plotted these data here. So we have all of the archive data, which is the 1970 to 80 archive. So this is the one from the Adrian Bath report that I was telling you about before. That was the 1980 report. This data had geochemical parameters, but it didn't have spatial coordinates. So I can use it in the graphs, but I couldn't use it in the maps, which I'll show you in a bit later because it didn't have any coordinates. Kirkpatrick from 1969, this was a study into thermal springs. So all his data are thermal spring data, which is important. And again, you'll see why in a minute. And I've plotted them per, the colour represents the temperature of the groundwater. So each of these groundwater samples here all have an associated temperature, and they've been plotted per temperature. So you can see here, this black curve is the fluorite equilibrium curve that I was telling you about. So generally speaking, it should be under, on, or not significantly over this line for it to be in equilibrium with fluorite. And this line here is the World Health Organization limit. That's 1.5 milligrams per litre, and this is the Malawi limit. This is 6 milligrams per litre. You can see here there's quite a nice correlation, for example, with the high temperature ones from our survey. So sorry, I should have said that. So the bottom samples here, the circles, these are data from our research group, which were collected between 2016 and 18, and they were also used to help to determine the validity of some of the archive data. So they've been plotted against the archive data just to show the trends there. So you can see here that there's above 6 milligrams per litre seems to be where the majority of hot springs plot. And again, that will make more sense as we go on. This is just a quick plot to show you, again, the temperature sensitivity, which I spoke about just a second ago. We can see here the southern region hot springs. Now the southern region, again, I'll just go back to the two Rift Valley environments I mentioned earlier, the part of it in the northern and central regions of Malawi, which is submerged below Lake Malawi, and then in the southern region, which is the onshore expression of the Rift Valley. So I tend to treat them separately. So on this graph, you can see here that I have green diamonds for other hot spring locations and red circles for the southern region hot springs, just to show that there are different environments there. But anyway, the most important thing being this line is 32 degrees Celsius. So we can see here that anything on or above 32 degrees Celsius is a hot spring, which is the filled symbols, and anything below that is not a hot spring. So there's again a nice correlation here with temperature. Now these are just preliminary investigations based on basic geochemistry and temperature that I was performing with the archive data, just to try and get a sense of what the main sources of fluoride were in Malawi. So the results are the fluoride has been documented for the first time in Malawi, and I'll say national scale, but it's more regional because we're dealing with this section here, the onshore section of the Rift Valley, because as you can see here from the numbers, I've split the samples into the different regions and then for all, so you can see the sample numbers here are very small in comparison for the other two regions than they are for the southern region. So that's why I tended to, in this particular part of the study, I focused on the southern region. So you can see that this graph quite nicely shows that there are two distinct source types of fluoride in groundwater. There's hydrothermal, which is the hot springs, and they're associated with hot springs, obviously, and location to faults. And then there is lithological, which is essentially everything else in the groundwater sample. So you can see here I have split this into low, slightly elevated, and excessive, just so that there's some concentration bands so that we can kind of deal with these easily. So elevated, which is between 2 and 6 milligrams per litre, you're looking at about 4.5% of samples, which isn't very high. And for excessive, which is 6+ milligrams per litre, you're looking at about less than 3.5% of samples. So it's not as high as it is in other East African rift countries, with Malawi not being as volcanic. It's not volcanically active at all, although it does have hydrothermal activity, but it's still locally significant. So we'll move on to that. So in summary, groundwater fluoride documented, 1,365 samples in Malawi groundwater at the southern periphery of the western branch of the East African rift system, which is a kind of a unique location. Fluoride greater than 6 milligrams per litre at 3.4% occurrence, less than East African rift system elsewhere, but locally significant. Geological control, excessive greater than 6 milligrams per litre, tends to occur in hot springs greater than 32 degrees Celsius. Actually, almost all, I think all of them did. And then the hydrochemical control is the fluoride control of fluoride calcium in the groundwater. There was a pH correlation. It wasn't as strong as you saw in the temperature graph, but essentially the higher the pH, the higher the fluoride concentration in the groundwater. And one of the main things that came out of that was that the most obvious groundwater fluoride from a management perspective is the greater than 6, which is the hot springs. The one that's going to present more of a challenge for Malawi is the between 1.5 and 6. So that's between the WHO and the Malawi guideline standards for fluoride in drinking water, because they tend to be lithological in nature. It's a kind of generic source. It's very difficult to manage that, and that's where most of the concentrations actually range. So that was the key management challenge that was kind of came out of that. So things to note as we go forward. I've recognised that high fluoride may be a result of hydrothermal groundwater mixing with shallow groundwater and sediments. Now that's important, and we'll get to that in the fourth section. I made a preliminary estimate in this particular study of the number of people that would be affected by high fluoride. So the number is 283,000. That's based on the data that I've just presented to you and an average number of water points, users per water point from Malawi. That's important. It's just a kind of a rough estimate which I made in this study, but that actually gets revisited and is much more specific later on in stage 3. So we'll get to that. Recognise that dental fluorosis data, so official medical data, incidence of dental fluorosis may act as a proxy indicator locations for high fluoride. And again, that's revisited later in the dental collaboration that I mentioned earlier. And I recognise the need to map geological or geogenic vulnerability, which again is revisited later. And that was written and published in Science of the Total Environment. So that was that section. The next stage was to develop a case study. So I wanted to develop a way to predict this nationally, like I said before, and my way of doing that was a case study. And I also wanted to quantify the human health link. So the first stage, and that was a source extent investigation. So I wanted to look at the source, the lithological, excluding hot springs. We get back to that later. This is specifically lithological sources of fluoride that we're dealing with here, because that's this is the troublesome management issue that I mentioned a minute ago, the 1.5 to 6 milligrams per litre range. It's difficult to manage. So I wanted to address that. So I was looking at the geological sources of fluoride and how far does that travel from source. This is just a little bit of background to the study area. It's in central Malawi. It's 13 kilometres by 9 kilometres, so it's a relatively small area. And it was chosen because the main aquifer unit is the weathered basement aquifer. The weathered basement aquifer is the most extensive aquifer unit in Glasgow. I think it's like 80% of the aquifers in Malawi. Don't quote me on that number as a guess. I'm trying to remember. I can't remember, but it's the most extensive aquifer unit in Malawi. So it made sense. If I'm going to be developing something that's going to be applied nationally, then it makes sense to look at that aquifer unit. The next most extensive aquifer unit is the basin sediments, and that again is dealt with separately, and we'll get to that later on. So this is the study area. It forms it's on the highlands between the Rift Valley and the plateau area behind the Rift Valley here. So this is the Lilongwe River, and this is the Llanthepe River. This essentially forms the border between both of these catchments. So recharge that happens here is flowing in both directions. In this particular study, I just dealt with on the Lilongwe drainage side of it, just to keep things simple. So we'll get to that. So this is just a little map I made of the groundwater levels based on data that we actually have. And this is just a basic map of the geology of the study, just to give you an idea. So again, we've got Rift Basin sediments here. This is the Rift Valley. This is the plateau behind the Rift Valley, and these are the highlands with all the faulting, as you can see. So weathered basement aquifer isn't covered by sediments. This is exactly as you think it is. It's just a weathered basement. So you've got basement rocks here. You have an oggen gneiss, which is granitic composition. Charnocatic gneiss and granulate in here, and then you have some basement syenite and some marbles in there as well. Okay. Oh, and that AB line is the line of cross section, which I'm just going to show you now. So these cross sections were developed. This top one here is just to give a profile of the weathered basement aquifer in the study area. So we're only really looking at the aquifer here. So the grey is the basement rock, and these are the weathered basement aquifer units. And it's to give an idea of how groundwater flows locally in the study area. So we've got that highlands here. Let me just go back and I'll show you, which is this part here, and elevation drops in this direction. And that's what you can see here. So we've got there's a lot of regional folding here because these are basement rocks. There's at least 2 stages of deformation associated with the Rift Valley. So there's a lot of linear folding. So that's what you're seeing here. These are linear folds or linear changes in lithology, which are caused by the geology. So this next one here is an idealized, we'll call it a cross-sectional conceptual model. It's not to scale. The top one is to scale, this one isn't. So this is just to show you the expression of how groundwater behaves within these little units here, within the weathered basement aquifer units. So I've got a dry season water table and a wet season water table. We have the 3 main lithology types, which are the oggen gneiss, the granitic composition, the charnocatic gneiss and granulite, and the hornblende biotite gneiss. Those are the 3 main lithological units dealt with in this particular study. These boreholes here are just to give an idea of the type of water that's been extracted from these boreholes. So for example, this one has elevated fluoride because it's in an elevated fluoride lithology, and it's abstracting water directly from the weathered basement zone. Here we have a granitic composition, and we'll go into the differences between those compositions and rock types in a minute. And then we have the main thing here to notice is the difference in the dry season water table and the wet season water table is that when wet season rains, these dry season water tables have isolated subaquifer units, I've called them, when the water level drops below these nice mound levels. So it's during the dry season, the groundwater in these units are isolated, but during the wet season, when the water table rises, there's room for some connectivity between those sections. So when we're talking about regional groundwater movement, we're talking about dissolution happening in the dry season and then some flushing down during the wet season, and over time that causes a little bit of progression, but not much. But we'll get to that again in a second. And this is just a quick look at the geochemistry of the study area. So the map here is TDS, dark color higher TDS, light color lower TDS. The highest TDS value measured in the groundwater samples from the study area was only 517. So we're not looking at it's not a huge range here, but that just gives an idea of where the recharge and the discharge zones are, essentially. And then these are the other geochemical parameters measured. This is Oggen gneiss, and this is Charnocatic gneiss and granulite. So this is the granitic composition one, and that's important to remember, as you'll see in a second. And this is the non-granitic one. So the most important thing to notice here is fluoride. This is the fluoride concentrations in groundwater samples located within that particular lithology, and then the same again for the Charnocatic gneiss and granulite, are an order of magnitude less when you look at the trend. And then important to note that the main driver, the main dominant factor for groundwater composition, chemical composition, is actually rock dissolution. There was no precipitation indication whatsoever, and very little towards evaporation dominance. So the dry season evaporation doesn't seem to contribute massively to the fluoride concentrations in groundwater. It seems to be completely controlled, or at least dominantly controlled by rock dissolution. So that was the purpose behind that, was to determine the extent from source to where we pick up this fluoride, and for where we collect it in the groundwater samples from boreholes. The extent of that isn't huge, but when a borehole is drilled into a lithology, the groundwater, generally speaking, in this aquifer has shown to be indicative of the location that it's drilled into. There doesn't seem to be much lateral movement here, although there is some. So this is just a map view of the fluoride concentration. So these are all the groundwater points that were sampled, and you can see here, this is the granitic composition. Again, gneiss, this is the only lithology which hosts the highest fluoride concentrations above 3 milligrams per litre. So the next stage was to try and to view that statistically. So these are the three different rock types here. Now, hornblende biotite gneiss was measured, but I tend to omit it a little bit later on because there was only 3 samples in that particular lithology, so confidence isn't high in the results from that, but I will present them, and you can see why that's important later. But the Oggen gneiss, so you've got fluoride concentrations here from 0.1 to 10 milligrams per litre, split per rock type, with the WHO threshold guideline and the Malawi threshold guideline. So you can see here that Oggen gneiss has significantly more chance or risk of abstracting groundwater with elevated groundwater fluoride levels than the Charnocatic gneiss and granulite does. So this was expressed as a risk map. So this was the purpose here, was to create this risk map, and it's essentially to repurpose the geology shapefiles, if you like, as risk zones. So the grade 2 is greater than 60% of groundwater fluoride abstracted containing fluoride concentrations greater than the WHO threshold, which is 1.5 milligrams per litre. So it's greater than 60% chance in these granitic composition rocks. This is the hornblende biotite gneiss, which actually is also greater than 60%, although there's only 3 samples in that particular sample set. And then the rest of it, the green, is the Charnocatic gneiss and granulate, which is less than 20%. So that's quite a significant difference statistically between those 2 different rock types. And it shows that these, I mean, there's only 39 groundwater samples here. So with 39 groundwater samples, this entire region, or this entire local area, can be mapped in terms of lithological risk of groundwater fluoride. So that was the idea. This is the prediction screening method, if you like, has been developed, and this is the expression of that. So in order to support that, I looked at the health link. So the first thing was survey data, which is the top part here. Now this was a survey which was conducted by the government of Malawi, coincidentally at the same time I was doing my analysis, and they had a question on their survey. The question was, does anyone in your household suffer from brown or black staining of the teeth, which is quite a question which is open to interpretation, but it's good qualitative data and it gives a good indication. So I mapped the percentage of yes responses to that question against each of the lithologies. So you can see here that the Auga gneiss, the granitic composition one, and the biotite muscovite gneiss have 41 and 40% percentage of those responses were yes, compared to the charnochitic gneiss and granulate, which only had 22%. So that's half essentially percentage yes, which those results reflect the geochemical analysis that say that the Auga gneiss has the higher risk of groundwater fluoride. So that was just a nice bit of qualitative data to support that. The second thing was a human health risk assessment. This is a method developed by the United States Environmental Protection Agency, and it's to develop a non-carcinogenic risk index for water points essentially. So they take into account various parameters: fluoride content in drinking water, daily water intake, average body weight, etc. And there's a really simple equation which calculates a thing called a hazard quotient. I've just shown the calculation here, but essentially what that is a number either above or below 1. If it's below 1, that water point doesn't have a risk of fluorosis. If it's above 1, it does have a risk of fluorosis, and the higher above 1 that number is, the higher the risk of fluorosis. So I performed that on each of those 39 water points, and these are the results. So I've split them between the three main lithologies again. Now, the adults and the older children aren't quite as relevant because fluoride causes dental fluorosis during teeth development. So it's younger children that are more at risk. So again, you can see the Auga gneiss has a 93.75%. 93.75% of those water points had a hazard quotient greater than 1, which means that for children aged 6 years and under, that's 94% of those water points are going to cause fluorosis in those children, which is a huge number. And then if we just skip the biotite gneiss because there's only 3 samples here, if we go straight to the other main one, which is the charnochitic gneiss and granulate, so we tend to, if you think of these rocks as granitic composition, non-granitic composition, so basement metasediments essentially, only 55% of those have a risk of causing fluorosis in children aged 6 years and under. So again, just another thing to validate the human health link between geology and fluorosis, and also to support the results that show that the granitic composition rock is higher risk, and that supports the development of the risk map there. So just to summarise that particular stage, the challenge was that groundwater fluoride occurrence in Malawi is geologically controlled. Some groundwater has fluoride above World Health Organization guideline values, and the government of Malawi rural groundwater quality standards require science-led policy for reduction from 6 milligrams to 1.5 milligrams per litre. So that's the policy aspect that I mentioned earlier on, which I won't go into too much detail. The hypothesis is that hydrogeochemical and hydrogeological data combined with human health risk parameters can be used to quantify geogenic fluoride risk in Malawi, which is exactly what was demonstrated there. So this is just a little conceptual model to show that. We've got the 2 main sources, which are deep and shallow, or hydrothermal and lithological, if you want to split it that way. So where you have a low risk lithology, which was the charnochitic gneiss and granulate, there's no health link there, or there's very little health link, but the main health link here is where you have an elevated risk lithology. So for example, the Auga gneiss in this case study was greater than 60% risk of fluorosis causing producing groundwater which has enough fluoride to cause fluorosis. And that's where the health link is. So that was kind of quantified on a local scale here. So the geological control on fluoride occurrence was confirmed by field data. The implications are national for similar hydrogeological environments, i.e. the weather basement aquifer, which exists nationally. And it facilitates mapping of geological fluoride risk zones, which is the important thing to remember here. The health risk link was quantified, and that in turn justifies policy review. And that was then published as a paper, a separate paper. So that's just the cover page for that. So we've went over the desk study, we've went over the develop stage, which was the case study to develop the prediction method and to quantify the link with human health. The next study was to adapt that method on a national scale. It's only useful to the Malawi government if they can do it on a national scale, and it's within their resources to be able to do that. So that was the next challenge. So this is what stage 3 is all about. So this is just a map to show all of Malawi split into the various catchment zones. So I mentioned before that some rocks have some lithologies have a higher risk of groundwater fluoride, and it was the alkaline igneous rock. So I wanted to compare that against global data from different places all over the world and see how that compared to my data. So that's what this is. These are just the references for all the papers where I found data that I could extract and put them into this graph. And you can see here that when you split fluoride concentrations per rock type or per lithological group, if you like, there's some quite clear differences. So obviously hot springs are the highest risk. I mean, the lowest sample there is above the World Health Organization limit of 1.5 milligrams per litre. So they are rightfully classified as excessive fluoride risk. And then the next on the list is alkaline igneous rocks, so your granites, your cyanites, that sort of thing. They, again, are much higher in terms of their risk of fluoride than other rocks. For example, sandstones and limestones tend to be much lower. So that just kind of gives a basis for comparison to what I'm about to go over. So the challenge here, actually the first challenge here was digital geology. There was no available digital geology files for Malawi. Now, in order for me to analyze fluoride versus lithology spatially, I needed digital geology files. So I had to digitize all of Malawi's geology. It was a significant task. It took me about, all in part-time, about a year and a half. And I'd done it basically from high quality scanned maps from the Geological Survey of Malawi. And this top one here is just to give you an idea of what those maps were. There were 10 of them. They covered the whole country. They were developed in the 1960s, although are surprisingly accurate, or perhaps not unsurprisingly accurate, but they were very accurate anyway. So those were georeferenced and put into ArcGIS, and then I was able to digitize over the top of them. I compared that with, I was able to compare it with topography from satellite images to correct for any errors there. To find, I was able to use the topography, for example, to map faults that hadn't been mapped on the original maps, and then any updates that I could find in literature. So this is an example of that. 2019, I think this paper came out. 2020. New faults were discovered. So on these maps had been mapped as terraces or terrace features, but it turns out that they were actually faults, and that was proven through ground movement measurements and various other things. So that's basically how I created these files. So I had a digital geological map of Malawi split into lithologies, which I could then work with relative to the fluoride. So that's the map itself split into the various different lithologies. So there was 84 lithologies altogether. Specifically, I used the same ones that were on the original maps. Those, just go back one slide actually. So these maps here, the original maps, they actually come with bulletins as well, which is a lot of text information on specific lithologies and mineralogies and things like that. So they were used in conjunction to create this. So that was the first step. The second step was from the original data set, the fluoride groundwater data set that I mentioned before, I wanted to extract everything that had spatial coordinates, at least spatial coordinates and a fluoride concentration measurement. There was about 1,030 altogether samples. All of them were located in the southern region, although the ones from my study were in the central region, which I just showed you a second ago, were added to that as well. So they were in the central region. and then extracted them from GIS per their lithologies, so that we could look at the statistical risk of groundwater fluoride concentrations per lithology, in order to create a map similar to the case study one that I showed you before, the risk map. So I've put each up here, shows you the individual lithologies where there was groundwater data, corresponding groundwater data. So I've also put the sample numbers in here. These are important because confidence is lower with a lower sample number. So for example, here n equals 3, I mean, it's 0% risk of greater than 1.5 milligrams per litre, but there's only 3 samples, so that may change with an increased data set, and obviously increased confidence in a sample number like that, 678. So it's really just so that that's for visibility, to show the relative differences in sample numbers there. On the left-hand side, we've got the groundwater fluoride concentration ranges from 0.1 to 10. Down the bottom, we have, so I've split these concentration risk factors into ranges. So we've got low, which is less than 10% likelihood of groundwater fluoride. I've abstracted from these rocks greater than 1.5 milligrams per litre limit. Moderate to low is 10 to 17% risk. Elevated is greater than 60% risk, and excessive is 100% risk. And as you can see, excessive is basically hot springs that has a category of its own. All of the alkaline igneous composition rocks, they're all greater than 60%. And in fact, those were the only rocks that were greater than 60%. And then everything else is below that. So between 17 and 60% risk, there was actually no lithological units whatsoever. So it was quite a jump here in terms of risk factors. So I think that just, again, it shows the significance of alkaline igneous rocks in terms of fluoride contamination. And then on this side here, we've just got the concentrations, the fluoride concentrations, and their relative fluorosis threshold. So below 0.5 milligrams per litre, you tend to get dental caries, which is actually fluoride deficiency. So a lot of countries will add fluoride to their drinking water or dental supplies if water supplies fall below that. 0.5 to 1.5 milligrams per litre promotes dental health, so that's the optimal range here. Dental fluorosis occurs from 1.5 to about 4. Actually, it occurs all the way up to the top, but before we get to skeletal fluorosis, which tends to occur about 4 milligrams per litre, and crippling fluorosis is anything above about 6 milligrams per litre. That changes from study to study, but these were from one particular study which produced data, which I was able to extrapolate that from. So this is an important graph, because this forms the basis of the map that I'm going to show you in a minute. So you can see 12 lithologies there. Each lithology has a sample number. Each lithology has a fluoride statistical risk factor, and the risk being risk of fluoride greater than 1.5 milligrams per litre, therefore will cause dental fluorosis. And it has the WHO drinking water standard here and the Malawi drinking water standard here. So you can see here that that's very obvious that that is far too high. That needs to be lowered to here in order for them to achieve SDG 6. That's just something that they're going to have to at least try to achieve. These proposed water standards phase lines are basically a proposal that I suggested to reduce it rather than just going straight from 6 milligrams per litre down to 1. That's unfeasible. So my proposal in this particular study, which was published and written with key members of government, actually, from the Malawian government, it was a proposal to reduce that standard over time via stepped progression. So that's what those are, but we won't worry about them too much in this presentation. This is like a cross-sectional conceptual model, just to show it's basically a visual representation of where these numbers are coming from. So here you've got the alkaline igneous rock represented by this red. So a borehole drilled into that, you're looking at greater than 60% risk of elevated fluoride in the groundwater. Here you have the moderate to low fluoride lithologies, which contains many lithologies. That's your 10 to 17% risk, and so on. So it's just to give an idea of where these groundwaters are coming from and what's causing these concentrations. This is, I suppose you could say, the Rift Valley or the Rift Basin sediment. So these are all drilled into lithologies or weather basement aquifer. This is unconsolidated sediments. And again, I'll get to the unconsolidated sediments as a separate aquifer later on. And then you have a hot spring here, which is the excessive fluoride, which I was talking about. So that's 100% of elevated fluoride. And then you have here, which I have coined a hidden hot spring. So it's a borehole drilled into sediments, which is abstracting water, which is connected to a hot spring, but there's no way, you can't see that, it's not visible at the surface. So this is just a summary of the different lithologies. So we have a group of alkaline igneous rocks, a group of basic igneous rocks. I've split them into these groups, and the reason for that is because if you look here, we have 12 lithologies which had corresponding groundwater fluoride concentrations. There are 84 lithologies in Malawi. So in order for me to be able to make this work nationally, I had to extrapolate a lot for lithologies where there wasn't corresponding groundwater fluoride. So I've done that by composition. So we're looking at granitic rock, granitic composition rocks here. So for example, we have granite, biotite granite, and oggen gneiss samples for them, but the other ones we don't. So I went through the bulletins that I was telling you about and the papers and everything, anything geological that I could find about these particular rocks, looked at the mineralogies, and if they had similar fluoride-bearing mineralogies, they get grouped into that particular group, and that's how I was able to extrapolate that on a national scale. And then this is an example of where I had to reclassify some lithologies. So for example, this one was classified as a cyanite, which is an alkaline igneous lithology, but it had a very low risk factor. I think it was 5%. This one here, yeah, 5%, which is really, really low. So that was a bit of an anomaly, because if it's a true alkaline igneous composition, it should be up here in the higher risk factor, and it wasn't. So it turns out that this was actually a metasediment that was intruded by cyanite, and it's undergone lots of deformation stages, and the cyanite is linear occurrences of cyanite which occur within the basement lithology, and they are of unknown thickness. So I've reclassified that to a metasedimentary lithology, because that probably reflects that low fluoride risk factor. And then this is so the next stage in that was I wanted to map the risk areas in terms of fluoride lithologically controlled groundwater fluoride, but I also wanted to produce statistics for people and water points on the same map. So the research group, which I done my research through, we have an ongoing project where we're mapping every single water point in the country, 120,000 of them altogether. So I was able to extract data for groundwater only water points, which are either functional or partly functional. And you can see here where these occur. So we've got boreholes, shallow wells, and natural springs. The not functional water points were counted separately because they can be fixed. So they still represent a risk, but we'll leave that for now. We'll concentrate on these three here. And this is just a graph to show the distribution of those between the different fluoride risk factors. So, sorry, let me just go back one. The most important thing about these water point data is that each water point, so 46,000, just over 46,000 of the 120,000 were the groundwater ones, which I used in this study. Each one had data on how many people normally use that water point, which was incredibly useful, because when I created this, which is the final map, I was able to calculate not only was I able to map the fluoride zones, but I was also able to calculate, or at least estimate, how many users and how many water points and how many users in each fluoride risk zone were at risk from elevated fluoride. So, for example, you've got the red zones, which are the elevated geogenic fluoride. So that's the ones that are greater than 60% likelihood of elevated fluoride. So that's these red zones here. That's all the alkaline lithologies. So boreholes drilled into these zones are of the highest lithological risk. So that's the second one here, elevated geogenic fluoride. So I was able to extract the data from that, the water point data. So there's 1,168 water points within those zones nationally, constitutes 2.3% of all water points, and you're looking at almost 250,000 people at greater than 60% risk. So that's what the real exciting part of this was. It's not just the risk zones; you can actually estimate how many people are going to be affected by these different zones. The excessive is the hot springs. So they've been mapped as site-specific zones as the little red stars. They're important because you may think hot springs is bubbling and hot, but actually they're not that. Most of the temperatures in Malawi aren't actually that warm. It's not volcanically active, so there's a lot of people use these water points for drinking because it seems attractive, because the water's clear, it's free from cloudiness and microbial contamination, that kind of thing. So a lot of people, it's attractive for people to drink, and people are drinking from these hot springs. So it was important to map them. So this is the main anomaly from that map. So the hot springs, this is all of the hot springs per the lithological unit from which they occur. So the biggest anomaly here is this is your alluvial rift basin aquifers. So we're looking at a range from 4 milligrams per litre to 20 milligrams per litre of groundwater fluoride in that aquifer. That's a really wide range, and it's probably not representative of the actual aquifer material. So that was that's a big anomaly from that map. So the next stage in this, so that stage was published. So that's the published. I published the maps, the geological maps. I also published the national risk map, and I also split that into catchment risk maps as well. Those are all published with that paper, so that they're tools that can be used by the Malawian government. Now, I don't know how I'm doing for time. I'm just noticing that it's 4 minutes to 6. I've got another part to go through, but I can actually finish here. So can someone advise what I'm doing, how I'm doing for time?
Yeah, good to carry on.
Good to carry on. Okay, fantastic. So that's the end of stage 3. So the method has been developed and it's been applied nationally, but with some obvious anomalies that need to be addressed. So the main anomaly is this thing here that I was showing you. It's the rift basin aquifer. It's an alluvial unconsolidated aquifer, and it's a really wide range of groundwater fluoride measurements, which probably isn't representative of the actual aquifer itself. So the next stage is to refine, and validate this method. So refine, which we want to address the hydrothermal fluoride anomaly, which I just mentioned in the rift basin sediments, but also to validate. So this is the collaboration with the dentists I mentioned, and that's really just to validate the human health link with confirmed medical data, something that hasn't been done before, at least not in the public domain. So this is a kind of idealized cross-section of the Rift Valley. So you've got the main rift zone in here, and then you have these plateau areas behind the rift, and then you have alkaline igneous intrusions, which are associated with the latest stage of rifting. So the anomalies that I was talking about, so this high range of groundwater fluoride measurements within the rift basin sediments, that's these rift basin sediments here. So this is the hypothesis being that they are the hidden hot springs that I mentioned before. So by that I mean hydrothermal water, which is moving up faults. It's heated at depth. It's transported vertically through active faults, and it discharges before it reaches the surface. So it discharges at the bottom of the sediment base, and it contaminates shallow groundwater, which is found in the alluvial aquifers. Excuse me. So obviously these hidden hot springs, as they've been coined, aren't visible at the surface. So it's going to be it was down to proxy indicators to try and identify them. Now, the purpose of this is to delineate these hydrothermal influenced water points or groundwater fluoride measurements from the ones from the actual alluvial aquifer, because then that refines the model and it provides a more accurate risk statistic for the alluvial aquifer. So the proxy indicators that we're looking at are geological. So is it in the Rift Valley? Is it near a large fall? Is it close by to other known hot springs? Because that's probably a good indicator that there are hidden hot springs nearby. Dental health is a main proxy indicator. So this is where the collaboration with the dentists came in handy, because they were able to visit schools. This is where they sampled school children. It was for their own study. They were looking at oral health, but they were one of the things they were documenting was dental fluorosis in children. So I was able to get a hold of their data when they were finished. They shared that with me, and I was able to plot these schools and their relative ratios of fluorosis and specifically severe dental fluorosis, because that was that's quite indicative of the excessive fluoride risk factor that's associated with hot springs. And then geochemical, what are the geochemical indicators? What is it in the geochemistry that indicates that this may be a hidden hot spring? There are other proxy indicators like temperature, but I didn't think that would be as relevant, because if it's a hidden hot spring, it's going to be mixing with shallow groundwater, which is cooler, so that's probably not a good indicator. And known hydrothermal activity nearby isn't as great, because if all of the hot springs in that area are hidden, then you wouldn't be able to use a known hot spring to locate them. So so to start with the geochemistry, or the geochemical proxy indicators, I used end member model data. So we have known hot springs here in the red, and we have no shallow groundwater with no affiliation, no connection to hydrothermal water whatsoever in the blue. So I plotted these over various different things, calcium against sodium, magnesium against calcium, everything, and these were the best relationships that I could come up with. So we're looking for very basic geochemical proxy indicators of hot spring activity within the study area, which is the southern region of Malawi. So you can see here there are some really nice correlations between hot springs and the sodium calcium ratio, or hot springs and the fluoride calcium ratio. They're very obviously separate. They're very obviously different. So the thresholds that I developed were greater than 2 milligrams per litre fluoride, less than 500 milligrams per litre sodium, less than 70 calcium, less than 30 magnesium. And the idea being that a groundwater sample has to match all 4 of those proxy indicators to be considered a potential hidden hot spring. This is just a summary of the fluoride concentrations from the model data and also from the archive data. So I'll just explain the archive data in a second. The model data is the one I just showed you on the map, on the graph, sorry. So shallow groundwater and hot springs, shallow groundwater, 95% was below 1.5. None of the hot springs were below 1.5. And if we're looking at greater than 6, or none of them in the shallow groundwater were greater than 6, but 58% of the hot springs were greater than 6. So it's just to give you an idea of the relative differences in those concentrations. Now, the first stage with the data collation that I mentioned earlier, I used that data again. So we used it. It was the data collation in the first section. It was the data that was used for the fluoride lithology statistical analysis in the third stage. And in this fourth stage, I used it again. And this was to then apply those basic geochemical proxy indicators to the archive data where it was possible, and to extract the ones that matched all 4 geochemical proxy indicators of hidden hot spring activity. So from 1,026 samples, 9 matched all 4. And that's this is them shown spatially. So the red stars are known hot springs. The white stars, which are numbered, are the 9 hidden hot springs, which were identified or screened from the archive data using the basic geochemical proxy indicators. So you can see they're very they make good candidates for hidden hot springs, because they're often located on a fault. They're often located next to known hydrothermal activity. Here we've got one on the boundary between an alkaline igneous intrusion and basement lithology, where the intrusion country rock boundary acts as a vertical conduit for hydrothermal water. And we know that because we have known hot springs next in that exact environment. So we have another one here. We have an alkaline igneous intrusion, and next to them you have hot springs, which aren't associated with faulting. So that's the assumption there, that it's that boundary that's acting as a vertical conduit. Over here we have hidden hot spring number 9, which is in the exact same scenario. It's right next to it's the boundary between those 2 lithologies. The rest of them all seem to be associated with faults within the Rift Valley and known hydrothermal activity, this one here. And in these ones, there's no known hydrothermal activity here. However, there are a lot of Chilwa alkaline province igneous intrusions, which are all these red lithologies here, and there are active rift faults. So they're a good candidate for hidden hot spring activity. And then this is the results from the dental survey. So this is just to show you what fluorosis looks like: healthy teeth, mild fluorosis, severe fluorosis, and this is the important one for the hidden hot springs. And these are the locations of the schools which were sampled by the dental team. And then we subsequently went back out to those locations and sampled the groundwater to corroborate the health data. And these are the groundwater samples. So those are this off-rift location here was the control group, because it's technically within the Rift Valley, and it doesn't have any alkaline igneous intrusions anywhere near it. This one is right on the Rift Valley fault, the data location, 2 schools here and 2 schools here in Machinga, which is actually within the Rift Valley. And this is the results of the groundwater analysis from those schools after we had visited after the dentists, basically. So the black ones are the ones within the Rift Valley in Machinga. The green ones are DEDSA. Those are the ones that are on the border of the Rift Valley, so actually right on the Rift Valley fault. And then the control group ones off Rift are the yellow ones here. So you can see they don't quite conform as nicely as the model data. However, there are some samples, notably these 3 here, and you'll see them in a different graph in a minute, which conform to all 4 geochemical proxy indicators. So some of them here conform to 1 or maybe 2, but only these 3 conform to all 4. So in terms of the basic geochemical proxy indicators that were developed earlier, that's the 3 that were picked out. And then this is just a little graph to show you how we determined the likeliness of each of those samples being a hidden hot spring. So Machinga has severe dental fluorosis confirmed by the dentist. It's in the Rift Valley, and it does have known hot spring activity nearby, so the hidden hot springs are likely there. Mzimba, which is the control group, doesn't have any of those things, so it's unlikely. DEDSA has severe dental fluorosis, and in fact was the worst case of severe dental fluorosis was seen at that school. It is within the Rift Valley. But it doesn't have known hot spring activity nearby, so it's probable, but we needed more information to confirm that. So I modified a Piper plot. I substituted chloride for fluoride just to show the fluoride ratios here. So the known hot springs, this is from the model data earlier, they all plot over here. The shallow groundwater samples all plot over here, and so the mixing trend would be anything in between here, which is where the hidden hot springs actually plot. So the blue dot is the model data for shallow groundwater. The red dots are the model data for hidden hot springs. And then everything else is these other scale samples. So those 3 samples here, which match all 4 geochemical basic proxy indicators, all plot within this hidden hot springs area. Plus 1 more, which actually didn't plot on all 4 geochemical proxy indicators, although it was very close. It was this one here. So the threshold here is 2. Which one is it again? Sorry, it's this one. The threshold is 2 milligrams per litre of fluoride, and this registered at 1.88. So it was very close. We can see here that that actually plots in that mixing trend, which was a really nice way to support that data. So then those were added to the map, the ones that were identified from the dental data. So anything that's identified from dental proxy indicators, geochemical basic proxy indicators, and geological proxy indicators from archive data and from the fresh data that we collected have now all been matched. All of those proxy indicators were mapped as potential hidden hot springs. So hot springs hidden beneath basin sediments, which are contaminating groundwater supplies. So that process allowed us to delineate those from those that were related, those that were influenced, hydrothermal influence samples from the Rift Basin sediments category from the 3rd section. That meant we could actually upgrade the risk factor or update the risk factor for unconsolidated sediments from 14% to 12%. So because we removed those hydrothermal samples, so it actually improved prediction confidence overall because new data has been added to the method, and because we have a more accurate risk factor for one of those lithologies, and actually for hot springs as well. And that was published as a 4th paper. So that was the refine and validate method. So just to go back to the aim, it was to develop a new, creative, cost-effective national solution for Malawi to predict groundwater fluoride accordance, which makes the best use of existing sporadic data. So the results show that the method can be effective with sporadic groundwater data where you can extrapolate based on geological information. Geology can be digitized if it's being applied in a country that doesn't have geological data. That can be digitized relatively easy. It just takes time. I done it with QGIS, but ArcGIS, but the same method can be achieved with QGIS, which is of course free. So that demonstrates that this method can be applied relatively easily for little expense, and that was just to show that the aim generally there had actually been achieved. So the novelty, local Malawi novelty, national groundwater fluoride data collation. So that hadn't been done before. Groundwater fluoride occurrence documented for the first time in Malawi. New creative method for predicting groundwater fluoride nationally, which didn't exist before. And geoscientist dentist collaboration, which was, it's the first time I've ever heard of it be done, certainly, but that was really useful in predicting hidden hot springs. And to quantify the link between fluoride and human health with medically confirmed incidence of fluorosis, which again also didn't exist for Malawi, at least not in the public domain. And the global significance is that there's a new research approach for predicting groundwater vulnerability to geogenic fluoride, which is applicable in the developing world. And there's a new understanding of fluoride occurrence in the peripheral rift location. Impact. It speaks for itself. It's a tool to evaluate groundwater infrastructure assets for fluoride contamination towards SDG 6.1, groundwater fluoride target. So this is something that's happened since these maps have been made. The government has access to this method and these maps since that have been created, and they have now been able to create or to develop a target related to fluoride, and that's that 80% of households in fluoride-prone areas are protected from tooth decay by 2026. Without the maps created within this particular study, they simply didn't have the information or the resources to make that a target, and they now have, and that's a specific target to come out of that. Rewriting drinking water standard and oral health policy documents to include fluoride contamination sources and target fluorosis remediation efforts. So that's something that didn't exist in the standard documents before, and can now be included as a contamination source, and something which will include mitigation efforts or mitigation. I can't think of the word there. And also there was a cross-disciplinary IDCP funding proposal for deep drilling into carbonatite cores. This is something that our research group was approached by a research group looking to do that, and they were attracted to us by the work that our research team had done on fluoride in Malawi specifically, so that was another impact. And then globally, the things that I've already mentioned, we now have an inexpensive and easily implemented tool for predicting and managing groundwater fluoride contamination. And countries globally can now manage groundwater infrastructure assets for fluoride contamination, allowing them to achieve SDG 6 targets and update policy where before this would have not been possible within the 2030 timeframe. And that is it. Apologies if I went a little over time. This is my first ever lecture, so it went a little. I tended to ramble on a little bit, but that's me. Thank you for listening.
Thank you very much. That's absolutely superb. Do we have any questions for Mark at all? I'll kick off if there aren't any others. In terms of mitigation, so if a local supply is found to be elevated in fluoride, and you can't put there isn't an alternative aquifer source within that region, how would they actually provide mitigation in terms of alternative supply?
No, that is a significant challenge for the Malawian government. So if you're looking at in the third section, which was the third paper, I go into a little bit of detail about possible mitigation things that can be done to mitigate that. So if you're living in close to the border, for example, between one lithology which is high risk and one lithology which is low risk, then you could cycle if it's feasible, if it's physically feasible. Then you could 50% of your water could come from that water hole, and 50% could come from another water point, and then you're halving your overall exposure. There are various, essentially, you can't fluoride removal has been attempted in Malawi and it's never really been particularly successful, so it's not really an option. So the main mitigation method is replacement water supply. So that's the only thing that you can really do. So in terms of local people doing it for themselves, then the cycling method that I mentioned, if it's physically feasible. If it's not, I honestly I couldn't say. I mean, piping water in from another area would probably be the best bet, but that's obviously expensive. I couldn't say, but yeah, its removal isn't usually feasible. So replacement water supply is the go-to method.
Thank you. Any other questions?
Yeah, I have a question, if I may. I've always been intrigued, coming back to Britain, by, well, it's known as Derbyshire Neck. And it was a sort of goiter that was prevalent, I think, in parts of Derbyshire that seemed to correlate to areas of high fluoride or high fluorospar, certainly within the mineralization within the Peak District. And I know the official explanation is said, oh, well, Derbyshire is a long way from the sea, so they have less opportunity to get iodine. And the suggestion is that it's effectively a lack of iodine that was causing the Derbyshire Neck. But I've often wondered if it's high fluoride, is the fluoride some way competing with the fluoride in the to cause Derbyshire Neck? I'm wondering whether or not you have picked up in the areas of high fluoride, is there any indication of increased goiter or associated compromise of mental faculties and so forth?
I'll be honest with you. I did not come across that particular condition at all in my studies. In terms of iodine as well, I didn't have, most of the data I analysed didn't have an iodine component, so it's not something I actually looked at, so I couldn't tell you. I honestly have no idea.
Okay, thanks. I don't suppose by any chance you or anybody listening, does anyone have any idea of the fluoride concentrations that would have been prevalent in the Peak District before water was piped in? No. Okay, thanks. Thank you.
Any other questions at all? So if not, yeah, thank you so much, Mark. That was really interesting talk. And clearly you've spent a lot of time putting those slides together. So thanks again. And yeah, if we wind the call up now, I'll just stop recording.
Fantastic, thank you.